this chapter is about substitution reactions, and let's just get to the problem. Draw a plausible mechanism for this transformation. So in other words, we have to draw the arrows, curved arrows, and the electron flowing throughout the reactant and product. And looking at our reagent here, we have potassium terbutoxide, and we're gonna have the we have a very strong base that can also be a strong nucleophile. So I'm gonna draw the lone pair just to show that we have a minus charge here, and that's gonna eventually cleave off the hydrogen from the left hand structure. And what we see is that everything is preserved except this part is not really. You will see that's the only difference you see. The rest are intact. So also you have to notice that there is the implied hydrogen in this sp3 carbon here. Okay, and the chiral center, this chiral center has all different groups, therefore it has to have the the wedged hydrogen, because on the next to it we have a dashed line there. And looking at this, the terbutoxide can act as a very strong base, so he's gonna come and grab a hydrogen, and then in turn it's gonna create a nucleophile on that carbon. Why do we have to do that? Well, we need a nucleophilic center over that carbon so that we can form a bond which is gonna attack that alpha carbon connected to that bromide, and then we're gonna have a leaving group, and thus we are happy with the new ring you see up there. So when this happens, and I can draw our intermediate structure. Okay, the rest of the stereochemistry is preserved, so you just have to copy that down carefully. Okay, so far this is what I have. Okay, I need to have the minus charge over there, okay, which signify that this is gonna be a nucleophilic center. Now this lone pair is gonna attack our alpha carbon, and then in turn that's gonna create a leaving group, and this has to be SN2, by the way. I forgot to mention that earlier, because we have a primary carbon here, or primary substrate. I know this is tethered structure where nucleophile and electrophile, or the substrate, is connected, so it's tethered, but still the principle behind SN2 doesn't change. So for SN1, we learned that due to the hyperconjugation, that the tertiary carbon or tertiary substrate is preferred, but here we have a primary, therefore SN2 reaction is fast, so it's favored in this case. Well, once you lose that leaving group, loss of a leaving group, and we just want to have this. Just remember that the stereochemistry has been preserved, and then you might wonder, why do we have that wedge on the new bond? Well, again, just like I said before, the sp3 is still not changed here, so we have to preserve the stereochemistry that conforms to this structure. So that's it, guys. Thanks for watching.